Today we're going to learn about dilations and how to perform them and identify them. A dilation is a transformation that changes the size of an image. The scale factor of a dilation describes the size change from the original figure to its image. It is an enlargement or stretch if the scale factor is greater than 1. It is a reduction or shrink if the scale factor is less than 1. You may have heard of the word dilate, like when your pupils dilate. However, a dilation in mathematics could grow bigger or get smaller, whereas dilate, when we're talking about our pupils, usually only refers to them getting bigger. On a graph, here's how we can see the scale factor in a dilation. So each image point is the scale factor times as far away from the center of dilation as its pre-image. So we've talked about distance with reflections. This time the distance is getting bigger or smaller, and it's increasing, it's multiplying by a certain number, but it's not going in the opposite direction like it does a reflection. It's going the same direction. The center of dilation that we're always going to use for this unit is the origin, which is the point 0, 0, the center of the graph. So because it's 0, 0, we can graph dilations and we can use the rule that we just multiply each coordinate by the scale factor. So we're going to call the scale factor C, and we multiply that number times x and y. So C is the scale factor. So we're going to do a couple examples where we perform the dilation. And it's actually easiest to use the rule for a few times until you get used to it. So first we're going to dilate from the origin with a scale factor of 1/2. So our transformation rule will be xy arrow 1/2 x and then 1/2 y. I'm going to write all the coordinates of my points. I wrote A, B, C on this table, but it's actually J, K, and L. So let me change those real quick. J, K, and L. Okay, so the coordinates of J are 2, 8. Then K is 8, 6. And then L is 6, 2. So now we're going to apply our transformation rule. I'm going to show my work up here so that you can see what I'm doing to all my pre-image coordinates. I'm going to put x and y from each coordinate into this rule. So I'm going to put, for j prime, it will be 1/2 of 2 and 1/2 times 8. Now, 1/2 is pretty easy to find out in your head, but you're going to deal with some fractions that might be a little more difficult. So there are a few ways that you can do this. You could do fraction multiplication, which means that you're going to change all your whole numbers into fractions by putting a 1 underneath and then multiply straight across the top. This becomes 2 over 2, which equals 1. You could also change the fraction into a decimal and then multiply it that way in your calculator rather than having to enter it as a fraction each time. So you would put 1 divided by 2 in your calculator and get 0.5 as your decimal, and then you just put 0.5 times all of the coordinates. So here's my first one. I got 1, And then 1/2 times 8 is 1/2 times 8 over 1, which equals 8 over 2. 8 divided by 2 simplifies to 4. So my first coordinates are 1, 4. Now I'm going to actually shorten my process because 1/2 is really easy to calculate in your head. You just divide the number by 2. So we're going to do k. K prime is 1/2 of 8 and 1/2 of 6. So 1/2 of 8 is 4 and 1/2 of 6 is 3. So those are my new coordinates. And then L prime is going to be 1/2 of 6 and 1/2 of 2. And 1/2 of 6 is 3 and 1/2 of 2 is 1. So here are all my new coordinates. I'm going to write them down in my table for you. Okay, now I'm going to graph J prime, K prime, and L prime. J prime is 1, 4. K prime is 4, 3. And L prime is 3, 1. If you're just eyeballing this and you're just like, okay, I'll go half the distance, make sure that you're going half of how much it goes in both the X and Y directions. One way to check that you did your dilation properly is remember they have to be in the same direction. So we're looking at the direction from the origin that J prime and J are. They're both on the same line, so that means they're both in the same direction. Same thing with L, and I think same thing with K. It went up 3, right 4, and then up 3, right 4. So that is on the same line. So that's how you can check. Now we're going to find out, is this congruent, similar, or nothing? When we compare the angle measures, let me get rid of my little lines so that we can see the shapes better. When we look at the angle measures, I look at J, K, and L. J looks to be about the same measure. K is also the same measure. It looks like it's a little smaller than 90 degrees. And then L is looks like it's about the same measure too. So our angle measures are the same. Our size is very obviously different, and our orientation is pretty obviously the same. Like the shape just got smaller. K and L didn't swap places or anything. So these shapes, because they're different sizes but they have the same angle measures, they're what we call similar. So it's like the exact same shape, but you just made it bigger. That's all you did. Okay, let's go ahead and do it with a scale factor of 2 now. So I'm going to do this a little bit quicker, and I'm not going to do as much work on this one. So our transformation rule, now we just write 2x and 2y, and then we're going to put in all our coordinates. Now I'm going to double each of those coordinates to get the image coordinates. Okay, I think I doubled all of those correctly. Okay, yeah. So now it's pretty easy to just graph all of those coordinates in. Make sure that you are labeling them as you do. Okay, T prime is 8, 4. And V prime is 4, 2. This is kind of wacky weird because one of the sides connects onto the original, so that's kind of cool. When we compare the angle measures, they are also the same. The size is different and the orientation is same. So these are similar. Anytime you do a dilation, you'll end up with similar shapes. They will not be congruent because they're obviously going to be different sizes. And congruent, they need to be the exact same shape essentially in order for them to be congruent. Let's go through how to identify the dilation that occurred. The hardest part of this is going to be figuring out your scale factor. So in our function, we take a point and we multiply it times whatever the scale factor is to get our new point, right? We're going to say this is x prime, y prime, even though we don't usually call them that. So now when we do this, we're going to go backwards to figure out what the scale factor is. And if I'm doing that, if I have c times a number equals a different number, we're going to call it z. Then I need to divide by that number to find out what c is. So we're going to divide the image by the pre-image. So divide the new shape coordinates by the old shape to find out what the scale factor was. Okay, I'm going to do it with n and n prime. So my n coordinates are 2, 2, and my n prime coordinates are 5, 5. So I need to find out what multiplied with n to get n prime. So I'm going to divide the n prime coordinate by the n coordinate, and they're both the same, so it's pretty easy to do. So when I divide it, 5 divided by 2, that's it. That's the whole scale factor. You don't actually need to simplify this. It doesn't simplify at all, so we're just going to keep 5 halves as our scale factor. I'm going to put 5 halves x and 5 halves y. Right. So you can check this by looking at other points. So these are all kind of in weird places, like they're in the middle of squares. So I'm going to take g and I'm going to multiply it by my scale factor, and see if I get g prime. So g is 2, negative 1. And I'm going to multiply it times 5 halves. So 2 times 5 halves and negative 1 times 5 halves. And see if I get g prime. So according to this, my new g prime should be 2 times 5 halves. Okay, when I multiply that, it ends up being where the multiplying by 2 and dividing by 2 kind of cancel. So this is going to be 5, and then this is going to be negative 5 halves, which is like 2.5. So g prime is 5, 1, 2, 3, 4, 5, and then negative 2.5, which it is. Huzzah, we did it right. Okay, so our verbal description is just going to be what it says for 1 and 2. What does it say? It says dilation from the origin with it. Okay, all of these are going to be from the origin. So we're going to say dilation with a scale factor of 5 halves. Okay. Now let's go through number 4 and see if we can do it. I would recommend that you figure out what your old and new shapes are before you do this, so that you don't take special note where the primes are, because sometimes my students always think that it's going to get bigger. But this one doesn't. It actually gets smaller. So I'm going to take f and see what happens to get f prime. So f is 4, 4. And f prime is 2, 2. So now I'm dividing the new by the old. So 2 divided by 4 equals 1/2. Okay, I'm going to write that that's my scale factor up here. But let's just check with another point. Let's do g. So g is 4, 1. And g prime is, what is that, 2, 1/2? Okay, so does g times 1/2 equal g prime? 4 times 1/2 is 2, woohoo! And 1 times 1/2 is 1/2. So that is correct, and we write that it is a dilation with a scale factor of 1/2. All right, thank you.